So for our next paper, we have a representative for Shovon, I believe. Okay, excellent. Who's going to be presenting here on the paper is called Towards a Cognitive Metric Using Normalized Transfer Entropy. And you are Dr.
I'm Nandagopal.
Nandagopal. That's Nanda and Nandagopal will be presenting today instead of Shovon, and let's just get set up here.
Well, thank you very much for the introduction. I think the previous speaker gave me a little bit of a lead. I'm going to talk a bit more about the EEG. I'm going to talk about measuring cognitive activity in EEG using transfer entropy. It's a new discriminant. Actually, the paper is written by one of my PhD students. Shovon is the first author. And his work is basically, this work is part of a broader research program on cognitive neuroengineering and computational neuroscience that I lead at the University of South Australia. Now, here is an outline of what I intend to share with you this afternoon. Motivation. Why are we doing what we are doing? And talk a little bit about, I think since Sunday we talked a great deal about big data, networks and networks and networks. And I'm going to talk about human brain as a big data system. I don't know, most of you realize that as we walk around, we carry enormous amount of data in our brains. It is a complex data system. So I want to start from there to outline the problem space. And the previous speaker spoke about a problem space where about 1 to 2% of the population have got the problem of epileptic seizures. I'm going to talk about a problem which 25% of the population is going through that problem. Okay, then I briefly touch on functional brain networks, which is the backbone of the analysis I'm going to talk about. And then a little bit about transfer entropy, which is, I think the first speaker this afternoon spoke about Shannon's entropy theory. So I'm building on that one. And then talk about how do we really stimulate ourselves, stimulate our cognitive brain so that we can solicit a response, so that we can understand what goes on when the mind starts thinking, mind starts processing, our brain starts processing information perceived from external world. That's what I call cognitive function. And then I present some interesting results, and then I conclude. So that's the agenda. So depending on how much time I go. Okay, I mentioned that 1 in 4 among us in this room have got mental disorder. Don't get alarmed. This is the World Health Organization December 2013 report. 25% of the population has got mental disorder. This is an alarming thing. The government is they're totally looking at globally about $2.5 trillion spent annually to address this problem. And they're projecting the problem is going to escalate to somewhere around $6 to $7 trillion in 15 years' time. You can see the scale of the problem we are really dealing with here. And also, if you look at US, UK, Canada, Australia, and Western Europe, the mental disorder-related issues really rank number 1, causing illnesses that really stop people from going to work. Again, look at the productivity problem, impact on that, and the cost to the government. And most alarmingly, somebody is committing suicide every 40 seconds as we speak due to mental disorders. It's all about the mind. It's all about how we behave, how we process information. It is the cognition. It is a cognition which really encompasses attention, memory, processing, fatigue, endurance, emotions. So that's an issue. As it relates to cognition or impairment of cognition, that really contribute to most of the mental problems. So my interest in trying to look at this problem a bit more closely. So I mentioned about this paper I'm going to present is part of a broader research program that I lead. Number one issue is how do we understand and measure complex human cognitive function through application of advanced signal processing, computational techniques, visualization, complex data modeling from EEG, the electrical activity of the brain. And also, most importantly, where we want to go, we want to explore and methodologies, techniques and methodologies, and hence develop some technology that we can go. Some technology like a simple iPod or phone that people can carry. They don't have to carry anything extra. That could help them to continually reinforce their brain, and keep them alert. And I don't want to use the word alert, but the technique which are looking at to augment the cognition, to improve the performance, the cognitive performance of the brain. So that is our goal. And hence we think that kind of augmentation could really overcome cognitive impairment people suffer, and hence try to contribute towards reducing mental illness and mental disorders. Such is the broad aim. Talking about human brain, it is a complex adaptive system. I know we talked about big data system. I don't know whether we realize we have something like 100 billion processing nodes in our brain we carry with us. 100 billion of them, at least. And each one of those nodes, the nerve cells or neuron, what we spoke before, can connect up to 10,000 other neurons. So if you do a little sum, what we have inside our skull is something like 100 trillion interconnections. A communication network inside our brain much, much larger than the communication network on this planet Earth. You can comprehend how network really operating inside. So what we are trying to do is, can we do a bit of an information processing in that complex network inside our brain? And that is that complex network functioning or lack of functioning causing the mental disorders. Okay, I don't want to talk a lot about EEG. We have let's see, this works. Once you stick electrodes, I think I'll use, it's not switched on, I think, yeah, it should work now. Once you stick on electrodes on the scalp, then you can record EEG. You can record hundreds of channels if you want, depending on how much money you have, how many electrodes you can stick on. Each electrode can pick up the ongoing electrical activity of the brain underlying the electrode. It's not picking up a single node, it's picking up millions of nodes, clusters of neurons underneath, and you can pick them up. Okay, so what do you do with that? If you want to really go and find an activity related to the cognitive function of the brain, when you start thinking, when you're looking at a screen blank, you can record some activity, and suddenly you start thinking or solving a problem. And I ask you a problem, subtract 17 from 222, immediately your brain goes into problem solving mode, cognition taking place. So what goes on? Detecting that from this kind of signal there is like picking a needle from a haystack. That's how complex the problem is. So what we want to use is, I mentioned before, communications theory. We have a lot of advancements we have made about communication theory. We can detect who is talking to who in the web. We've got millions and millions and billions of nodes, people talking to each other. We have technologies to do that. Can we really apply that? Therefore, my interest is convert that EEG signal into a network, a communication network I call functional brain network. Each electrode is simply picking up transactions going on in the brain in that site. So if you're able to detect the changes, a relationship between two electrodes, two nodes, then we can link them. And the strength of the relationship really gives you the link weight. So that way we can connect every electrode with every other electrode, then you get a functional brain network. Once you have got that one, then you're able to really apply all the already developed technologies, techniques, and methodologies to really information process in the brain and see whether we can go and detect that very micro changes happening in the brain when you are trying to do a cognitive task. So we have used transfer entropy in this process. Please give me a warning about 5 minutes before, because I have a notoriety or going the time. Thank you. Okay, I don't want to spend a lot of time on the mathematics. It's all there. When you have two random processes, random nodes having ongoing activity, I use here maybe electrode X, electrode Y, having entropy here and entropy there. This is the past values. This is the future value of this process here. Then this Y tries to transfer some energy, or this can try to transfer some energy. So can we detect that energy being transferred between two random processes, that is two nodes or two electrodes? If you are able to calculate, we can calculate using the Sandwich theory. So this is the transfer entropy, which is given as a function of the probability density functions. And so transfer entropy could be a very large number. So we need to really normalize that. And transfer entropy between electrode X to electrode Y is not the same as transfer entropy from electrode Y to X. You have to use a similar equation to calculate it. So in the context of EEG signals, transfer entropy basically detects the information flow between two transactions, two nodes. Okay, and also it denotes the influence of one node on the other. Okay, that's basically what it is. Okay, normally when you measure transfer entropy, there's a lot of noise there. The standard practice is you shuffle the Y series, got 5 minutes. Okay, I speed it up. And you shuffle the one of the series several times and take an average and detect it, so got a noise reduced signal. And then you divide by the total entropy, so you get a normalized entropy, which is either 0 or 1. Okay, why we are using normalized transfer entropy? Because this has not been applied to measure overall cognitive load that an individual experiences while performing a particular task. This is the first time we are trying to use transfer entropy to apply to the brain signals in this way. Okay, I'll skip that one. And our objectives are really to design an experiment to systematically stimulate the cognitive brain with increasing cognitive load, so that we can record and see whether we can measure the transfer entropy. So that's the basic aim. So we looked at 8 subjects initially, and then we have a baseline asking subjects to look at a screen with a blank screen or with a star in it, and then apply mild cognitive load using a standard psychological test called Stroop test. And in the Stroop test, you ask them, okay, you keep on flashing pictures there, and ask them to look at the picture, and the next picture will be a blank one. The third one, you ask them what was the first one they saw, and answer that. And similarly, the medium cognitive load, one back Stroop test with go, no go. If there is an yellow signal, don't respond. Okay? And then a moderate cognitive load with auditory distraction. When you have a moderate cognitive load, when they're trying to answer your question, you introduce an audio distraction. So that puts enormous cognitive load. Similarly, you can also put a visual load over and above that. That way, you have a 5-level cognitive load you can apply and see whether you can measure it using the complex signal processing and computational techniques. I think I mentioned the process we had gone through, skip that one. This is a standard data acquisition process. And this is an analysis framework we have developed in our laboratory, Cognitive Neuroengineering Laboratory, which is available for sharing, where you have, it's basically a software suite where you record, you really acquire data, either normal data, you stimulate them using a Stroop test, psychological Stroop test, or stimulate them using a driving simulator, or stimulate them using a flight simulator, making them to fly an aircraft. And then you pre-process, remove everything you don't want to see, and then you apply various techniques here. Transfer entropy. Once you have got the transfer entropy generated, you can develop a huge database, a graph database. Once you got the data in that form, then you apply a whole raft of mining algorithms to go and detect and track change, and then you visualize it. Here is a simple test. One of the social, we also spoke about social networks since Sunday. I use social network parameter like connectivity density, the actual number of edges, a portion of the total number of possible edges, and how well as individual node is connected there. And if you look at here, in this chart here for 6 subjects I indicated here, this is the eyes open, mild cognitive, medium cognitive, and then moderate, and then extreme cognitive load. In all of the cases, as a cognitive load increases, this social network parameter called connectivity density increases. And also we use characteristic path length. That really gives a feel whether it's an integration process taking place when the cognitive function is on. And basically the characteristic path length consistently reduces as you increase the cognitive load. That means the new pathways are created in the brain, and also they're very close, the clustering, they're forming thick clusters. So this is again demonstrating a phenomenon of integration taking place within the brain cells. I think this is the same result using clustering coefficient. And you can also visualize that using our visualization technique using topo plots and 3D visualization. And the left hand, eyes open, mild cognitive load, yellow. The next one is moderate cognitive load, high cognitive load, this column, and then this extreme cognitive load for different subjects. So you can easily see how the cognitive load varies, some of the parameters we have chosen. The parameters change as cognitive load increases, so we were able to detect and track that one. That's what this paper is about. And we have done some statistical significance test using Toki HSD test. Again, you can see that as cognitive load states in the bottom for 4 different subjects, and the vertical is the mean clustering coefficient keeps increasing. So this is a good metric. We haven't seen a quantitative metric. Yes, I'm finished. This is my last view graph. It's a quantitative metric. We think we have come with the quantitative metrics. And so what? This approach can be used to develop objective quantitative metrics to measure cognitive activity. And therefore, we can use this as a tool to really measure cognitive impairment. And in safety critical situations like flying an aircraft or in submarines and so on, you can monitor the operator workload and send warnings. Thank you.
Does anyone have any questions? Yeah, question about that.
Fascinated by that. We've looked at this in terms of recovery from PTSD and looking at mutual information, advanced mutual information transfer entropy. So is that what we're thinking is a potential next step? We can identify where such shock has occurred and possibly intervene to enable improved recovery?
That's a very good question and comment, Simon. It is our real goal. I haven't mentioned in this program. I would like to acknowledge that this work has been sponsored by the Department of Defense in Australia in concert with the US Department of Defense. The idea is to develop a tool to measure cognition and cognitive impairment, and also to go the next step of can we really develop an intervention, some non-pharmacological intervention to really address PTSD as one of the mental disorders. And if everything goes well, we will be looking at the Australian Defence Force personnel having PTSD, and we'll try to use them to first measure the cognitive impairment levels. And we are also concurrently working on an adaptive cognitive neurofeedback system, which is already, we have started shakedown trials. And mid-January, we'll be starting on actual people, which will try to influence and change the brain patterns, cognitive patterns, and see whether we can improve the performance, cognitive performance of normal subjects first, and then demonstrate, yes, you can improve that. Once we've done that, then we're taking up PTSD.
We probably need to talk offline. Ladies and gentlemen, this is a really major issue in the US and the UK. We have huge waves of principally young men, young women too, who will be suffering from PTSD in the next 15 years. And it's some of the work we've been doing. So so Nanda, I'd really like to connect up.
Thank you, and also for others, I'm really open for collaboration, because I'm a great believer in sharing information and the burden sharing on one hand, and also not reinventing the wheel. Thank you.
All right. So in the interest of time, I think we will take other questions offline, but let's thank Dr. Nandagopal.
Thank you.